Hello everyone, my name is Hiroki Ohtsuji and I'm going to talk about the RMI high performance user level multi-threading on SPDK and DPDKs. This is our development team. Dr. Maider and Mr. Kato are responsible for development of multi-threading library. Mr. Kobayashi is responsible for internode communication with RDMA. And Dr. Sato is a manager of this project. Hiroki Ohtsuji is a speaker of this presentation. This is an agenda of our presentation. First, I would like to talk about the background of this project and why we choose a thread model parallelization for this project. Next, design and feature of RMI multi-threading library will be explained. In the following section, I will introduce optimization techniques and some benchmark results. Finally, I will talk about how we implement and optimize internode mechanism with RMI. Let's begin with the background of our project. There are 5 requirements for all enterprise all-flash array storage systems. All listed metrics are always important, but especially scalability is the most important issue of the system. In addition, recent products have rich storage services like deduplication, erasure coding, and cloud integration. We have to provide the better scalability for those services. And also, the hardware trend is changing. Currently, we have many core CPUs with dual or more sockets. Sometimes, we have more than 100 CPUs cores in a single node. In addition, we can use high-speed interconnection with RDMA, remote direct memory access, that can access remote DRAMs with minimal overhead. Moreover, cutting-edge storage devices are available. For example, Intel 3D XPoint and NVMe SSDs. From the viewpoint of software, now we have SPDK that offers kernel bypass architecture to leverage the performance of latest devices. And of course, SPDK can be the fact of storage development. We'd like to share the knowledge we learned from the 3 years practice of development of enterprise all-flash array research prototype with SPDK and RMI. Background continues. We faced 2 problems in the early stage of the project. The first issue is development expense and speed. A large project often hires more than 100 developers. A line of code reaches to 1 million. Not all developers are familiar with asynchronous programming. Even for experienced programmer, debugging takes a long time. Second problem is effective performance and scalability. Performance of a multi-thread application is not proportional to the number of CPU cores because of the parallelization overhead. In addition, there is no load balancer for CPU utilization ratio. Performance of the internal communication is also important because the all-flash array system comprised of multiple storage nodes. Therefore, we have added 2 pieces to SPDK 1612. One is the programmability of multi-threading programming for storage systems, and another one is RDMA-based internode communication, which is currently not supported by SPDK. This slide describes the requirements for programming framework in our case. A better programmability for industrial applications means that scalable code should be compact, comprehensive, and reliable. In addition, integrity with SPDK is an important issue. We use SPDK's basic services, including drivers, as is, to shorten the development period. Therefore, our implementation is compatible with other SPDK applications. I'd like to explain the reason why we choose the thread model for the framework. There are long-time debates in many communities regarding thread versus event model. SPDK and DPDK uses event model, as you know. Recent SPDK has just started to support the threading model, but as of the release date of the 16.12, it was not available yet. So we choose the thread model because we can provide blocking APIs like traditional POSIX operations to developers. Blocking APIs make code more comprehensive. There are existing successful examples of a multi-threading model. Web servers and web services with stateful sessions are often implemented with the thread model. Thread model is also suitable for all-flash array storage services because they are comprised of complicated and large codes. In addition, there are many states to handle hardware and software failures. Inter-node communication is another important issue for the storage system because it consists of multiple storage nodes. There are various communication purposes like I/O delegation to different nodes and metadata updates, maintain redundancy by mirroring blocks, and heartbeat for the high availability. The figure describes the typical communication operations of storage services. There are many interactions to handle the single I/Os. Basically, data redundancy constrains the scalability because there are various lengths of the message to handle. Now let's dive into the Rma architecture. This slide explains the design and feature of RMI. Our framework was named RMI. RMI is an acronym of Rocket Messaging Infrastructure. It means the library can process messages between threads in high throughput and low latency. Of course, it supports multi-threading. Especially, it offers lightweight user-level threads for low overhead. It also offers various synchronizing primitives that are similar to Java and Go language. RMI enables SPDK compliant so that no change is required to SPDK NVMe drivers and other extension drivers. In addition, RMI can provide dynamic load balancing that levels multi-core utilization ratio to exploit the maximum performance of many core CPUs. This figure depicts the overall architecture of the system. Green blocks are provided by SPDK. As you may know, SPDK covers from the drivers to storage protocols. As I explained in the previous slide, we made no modification to SPDK itself. Red blocks are our original implementation, RMI. RMI threading environment bridges BDEV abstraction and synchronous multi-thread support. Synchronous multi-thread support offers thread pool and load balancing mechanism, including synchronizing primitives. At the bottom of the figure, drivers are also enhanced by adding internal communication drivers that use RDMA verbs operations. In this presentation, there are two important topics. One is a RMI threading environment for thread level scalability. Second one is the RMI internal communication for better internal scalability. Due to the time limitation, we've omitted several things like RMI BDEV bridge API, detail of the load balancing algorithm, RMI synchronizing primitives, and quick assist accelerating drivers. If you have any question about the detail of these topics, please ask me later or send an email to the address. I'm going to explain the RMI threading environment and show some evaluation results. RMI's lightweight thread is based on L thread of DPDK 16.11. It runs M RMI user-level threads on N native threads. Usually, M is greater than N. RMI uses cooperative threads control policy so that the scheduler cannot preempt running threads. Programmers have to call yield function explicitly to run other threads. It is the same as the recently added feature to the SPDK. RMI offers different types of synchronization primitives. One is I structure, which is similar to Haskell's IBER and Java's feature. Other one is Q structure, which is similar to Java's blocking queue, and Go language's channel. Also, RCU semaphore are provided. RMI has an original thread pool with load balancer that provides a matching place among the thread and tasks. This is the key technology of RMI, and I will explain the implementation in the following slides. This slide explains how we implement the thread pool for RMI. We have to consider two issues to design thread pools. First one is limitation of memory footprint. If there are a lot of available, runnable threads in the system, it consumes huge amount of memory. It depends on the growth size of the stack of functions. Therefore, we have to consider the nature of target applications. And second one is locality. We don't want to waste the effectiveness of cache and reduce the number of context switching. So locality awareness is an important issue for thread pools. Existing task schedule method only uses either one of two methods. One is tasks themselves activate idle threads. Other one is active thread get the waiting tasks. Both methods have some problems. First one is locality unawareness because the tasks don't care on which CPU core the thread is running. The second problem is increased context switches to execute multiple tasks. Therefore, we decided to apply hybrid task scheduling mechanism to the system. This is the RMI implementation of hybrid task scheduling. We fixed the size of the memory footprint to 2 GB. We omitted the discussion of the maximum number of threads. However, typical usage of enterprise storage system does not generate millions of threads. RMI uses a hybrid task scheduling policy. It uses two methods explained in the previous slide. Active threads can some waiting tasks, and tasks also can take idle threads. A former one has the advantage of locality awareness, and the latter one can eliminate unnecessary context switching. We can realize locality-aware lazy binding of tasks and thread while keeping sufficient parallelism with the hybrid task scheduling mechanism. This is a sample code of RMI threads. Left side is caller implementation. The RMI exec task structure handles the pointer to the function. Right side is implementation of the callee function. Developer can define the function as a task so that the code became very simple and comprehensive. There are two policies for load balancing. There are two we consider the moving active running threads or moving runnable task in the thread pool. Both have pros and cons. Moving the active running threads, pros is load balancer can directly level the core utilization. However, it requires modification to the compiler or the operating system because the cooperative thread has a thread local storage, but keep it consistent requires some modification to the system and becomes incompatible with existing resources. So we choose the migrating the runnable task model to implement the load balancing. The pros is there's no limitation for C programs, including the open source library, because the thread local storage is not activated yet. So the cons is the load balancer can gradually change the core utilization, but we didn't any observed drawbacks of this method. This slide describes how we integrated the RMI thread execution environment and the original SPDK mode. The RMI thread scheduler overrides an SPDK reactor. They are running on each core. SPDK routing is running in the RMI main loop. It runs on the same context as RMI's thread scheduler. First, RMI pulls hardware and software queues to manage timers. Then, call SPDK reactor for basic storage functions. RMI does not control the SPDK internal things, so that there's no modification was made to SPDK. This slide explains the performance issue of RMI execution model. Software queues are used for various purposes, including RMI task queue, ready queue, and SPDK event queue. For the multi-thread environment, all of them are concurrent queue. It means that there could be multiple writers and readers for each concurrent queue. Therefore, it requires some mutual exclusion mechanism to maintain consistency. Basically, lock can make the data structure consistent. However, it also degrades the performance in many core environment. So we are using CPU's atomic instructions for most non-blocking concurrent queues instead of mutex. Of course, there is still a concern regarding performance degradation. Following slide will show evaluation results of our concurrent queues in parallel execution environment. In order to evaluate the performance, we run the round-trip test. Each CPU core has a single queue, so its model is a multi-producers, single consumer, so-called MPSC. This figure describes the steps of the round-trip test. Step 1, a thread add an entry to concurrent queue. Step 2, another thread running on a different CPU core get an entry. Then it add an element to the concurrent queue in step 3. Finally, as step 4, the thread gets the entry. We measure the elapsed time from step 1 to step 4. So we compare the result of this benchmark with RTE ring of DPDK 16.11 used by SPDK 1612 and Yukov's queue in L thread of DPDK 1611. This graph depicts the performance evaluation result of a ping-pong benchmark with RTE ring, which is the default concurrent structure of SPDK. X-axis is the number of active CPU cores, and Y-axis is the measured latency. Lower is better. As you can see from the graph, the latency with RTE ring becomes longer when we increase the number of threads, especially when the workload spans different CPU sockets. The measured latency was 68 microseconds with 32 cores, and the scalability is not good. RTT becomes 48 times longer when we use the 60 cores. This is a result with Yukov's queue. The axis of the graph was the same as the previous slide, and we evaluated the Yukov's queue in DPDK 1611 with the same way as the RTE ring. The figure shows that the latency gets 48 microseconds, shorter compared to the case of RTE ring. Scalability also gets better. The latency gets 18 times longer with 16 CPU cores. However, there is still performance degradation when workloads span more than 2 CPU sockets. This slide describes the discussion of the ping-pong benchmark. We observed that the hardware lock by multiple CPU on different sockets is quite heavy, so that we have to avoid concurrent queue running on multiple CPUs, not multiple cores. With the Yukov's queue, the latency gets better. However, we still need to improve the performance because the measured latency is still high. It was more than 5 microseconds in each way. And when we consider the overall latency of the storage system, we have to shorten it because more than 10 interactions between storage nodes to process the single IOs. In order to shorten the latency of concurrent queues, we developed RMI task queue. RMI task queue stopped using MPSC, multi-producer single consumer model, and uses SPSC, single producer. There is a single writer to the queue, so that we can eliminate hardware locks from the queue. SPSC queue can provide good scalability unless they are overflowed. when they are overflowed, the original RT link can store the incoming entries, and we never lose any messages. Of course, there is a hardware lock and performance gets worse, but we can still keep FIFO orders. This slide describes the performance with our RMI task queue. Compared to the result with RT ring and Yukov's queue, the measured latency results were 1/14 and half, respectively. The RMI task queue demonstrates good scalability. It achieved 12 times longer latency when it runs on 16 cores. It achieved super scalability. From this benchmark, we can understand that the RMI task queue can provide good scalability by providing efficient concurrent data structure that can eliminate hardware locks. In order to evaluate the RMI concurrent queue with more practical benchmark, we run prime benchmark on the RMI multi-thread environment. In the prime benchmark, 10,000 filter threads can run concurrently to find prime numbers from 10 million numbers. Due to the RMI pool capacity, the actual number of threads is limited to 10,000. We compared the result with the RMI library with the benchmark implemented with Go language. This graph depicts the performance of a prime benchmark with RMI and Go implementation. X-axis of the graph is number of cores, and y-axis is execution time. Lower is better. The left graph shows that execution time of RMI is always faster than Go implementation. The right figure depicts the speed-up ratio to know the scalability of two implementation. This is a relative performance compared to the case with a single thread. Except for the case with 32 cores, both cases achieve good scalability. We need further analysis regarding the scalability decrease at the 32 cores case, but currently the absolute performance is higher than Go's implementation. Next topic is internal communication optimization for better node scalability. Our system uses a network interface that supports RDMA, remote direct memory access, which can directly access remote memory without additional memory copies. Valve's APIs are commonly used for RDMA communication. However, it only provides asynchronous posting and polling style primitives. If we naively use Valve's API, all of RMI threads will call Valve's polling function. This model is inefficient and will degrade the performance, so that we decided to provide blocking primitives. Developers can use RDMA communications by just calling MMI send, receive, read, write, as if they are using POSIX blocking operations. This slide describes how we implement the blocking communication operations for send, receive, messages, and RDMA read and write operations. The figure shows what will happen when an RMI thread tries to issue a communication operation and waits for completion. First, an RMI thread posts an operation with post-send function of Valve's APIs. Immediately after that, the RMI thread tries to read an entry from iStructure. iStructure is a synchronizing primitives. That is similar to Java's feature as explained in the previous slide. And our RMI polling thread polls the completion of the operation at step 3. If the polling function returns an entry, the polling thread writes to the iStructure in step 4. After that, the read operation issued in step 2 is returned. It's a blocking operation. And the RMI thread continue running. This is a mechanism of the blocking messaging and RDMA communication based on RMI multi-threading library. This slide explains the implementation of blocking receive operation. It's similar to the other operations, but the receive queue entry has been posted by RMI communication driver. Therefore, at first, the RMI thread tried to read from queue structure for synchronization. In step 2, after a receive operation is completed, the RMI thread writes to queue structure in step 3. After that, the RMI thread resumes and receives an incoming message. We implemented the blocking RDMA and messaging operation with RMI. However, we faced another performance bottleneck. The bottleneck is a lock contention problem inside the Babs API. RDMA-capable network interfaces, including InfiniBand, uses queue pair. It's different from the task queue or queue of the RMI. Queue pair, so-called QP, to establish a connection between two nodes. QP has two different queues inside it. One is work queue, and another one is a completion queue. Basically, post-operation to QP is thread safe, so that it has a spin lock inside the library, and it affects the performance of inter-node communication. We solved this problem with a dedicated queue pair approach explained in the next slide. As explained in the previous slide, we have to eliminate the chance of lock contention inside the Babs API library. We generated multiple QPs for each destination node and CPU cores. The figure describes the connection topology of QPs that span multiple nodes. For example, QPs of node 1 core 0 are connected to QPs of node 2's core 0 and node 3's core 0. A thread running over a certain core cannot post entries to work queues of a QP on a different core because it's a dedicated queue pair. Therefore, each QP receives a request from a single thread. Then we don't need an exclusive control anymore. We eliminate the lock overhead by using the dedicated QP for each core model. Here are pros and cons of this model. Pros is simply we can eliminate heavy mechanism for consistency. Another pros is Mellanox, a vendor of Hiroki interface, provides experimental operation that can disable hardware locks inside Babs operation. We can expect that this will reduce CPU usage for unnecessary locks. Cons is also simple. We need more QPs to establish connection within storage nodes. However, when it is limited to our case, it wouldn't be a problem because Mellanox adapter supports more than 100,000 QPs. Compared to this limitation, our design requires up to 1,200 of queue pairs because of the scale of the system. If the system consists of hundreds of storage nodes, it will be problematic, but it's not a regular thing for this type of enterprise storage system at this time. So I would like to explain the environment for the performance evaluation of inter-node communication. We use two compute nodes that are connected with 40 gigabits Ethernet. Nodes have two Intel Xeon Gold Skylake processor with 40 cores. Network interface is a Mellanox Connect 4EN that has a dual ports. We run a benchmark software to measure latency of inter-node ping-pong. It can measure the latency of both exchanging messages and performing RDMA operations. This slide shows the performance evaluation result of the ping-pong benchmark. In both figures, x-axis is the number of running RMI threads, and y-axis is the measured ping-pong latency. We compared the latency between the shared QP model and our dedicated QP model. The result graphs show that our dedicated QP model is scalable and possible to reduce the latency by 19% in both cases, RDMA read and send-receive messaging operations. We confirmed the good scalability of our shared QP model in the previous slide. We also measure the CPU utilization ratio of pthread spin lock function. As explained in the slide 35, Mellanox provides experimental flag that disables the internal lock mechanism for work queues. So we can reduce the CPU usage of a spin lock function, so now we can run more tasks on a single CPU cores. It will increase the throughput of the entire system. This is a summary of our entire presentation. In order to design a scalable enterprise all-flash array system, execution environment that has good programmability and high-performance multi-threading libraries are necessary. We explained how we tackle the performance issues. First one is lightweight user-level threads, execution environment with rich synchronizing primitives. Performance evaluation result reveals that the performance of RMI multi-threading library can exceed its of SPDK's default implementation. In addition, RMI is compliant to SPDK so that you can apply this optimization with minimal modifications. Second optimization is increasing the node level scalability and implementing low overhead RDMA communication library. At this time, we cannot show some typical storage performance metrics like IOPS, light, and read latency. But the optimization techniques we explained in this slide are fundamental and necessary for the scalable enterprise storage systems. We hope this presentation will help you make your SPDK project more comprehensive and scalable. Dr. Maeda and Mr. Kobayashi were supposed to be here today, but unfortunately they could not attend the summit. They welcome any question and feedback. Please feel free to send a detailed question to them. You can just send an email to this address. Thank you for your attention, and I'm happy to take some questions.
Thank you. Thank you for your great talk. I have a question for some components you mentioned to add into SDK framework. So would you have the plan to upstream some components like the RMI driver, I mean in SDK's driver layer? Thank you.
Question is how to keep the consistency between the RMI thread and SPDK. Is that correct?
No, my question is, are there any plan for Fujitsu to upstream the code of the RMI into SDK's drivers framework?
I think which slide is closely related to this one?
Yeah. I mean, so in the drivers layer, there are some new added components. So, will you have any plan to upstream the related code in SDK community?
Yep. At this time, I can't show any clear plan to commit to the SPDK source code. But in future, we can split the essential technology and we can publish into the public. We are planning to, but I can't say any exact date to do that. Sorry.
Other questions?
Any question? Okay, thank you.